Today inshallah we'll start chapter 10. Chapter 10 talks about two sample tests and one-way analysis of variance. In the last chapters we had already talked about one sample. And also we introduced how can we construct confidence interval for the mean or y. In addition to that, we perform tests about mu and y. And this chapter we are going to generalize our confidence interval and testing about two sample tests or more than two samples. For two samples, we are interested in the difference between either two population means or two population proportion. For example, suppose we are teaching students and we have males and females. And our goal is to test to see whether or not there exists a significant difference between scores of males and females. So in this case we have two populations, population A and population B. And for example, suppose we select a random sample from the first population and select another sample from the second population. And the goal is how can we construct a confidence interval for the difference between mu1 and mu2. So we are talking about mu1 minus mu2, or the difference between two population proportions, pi 1 minus pi 2. Sometimes there exists more than two populations, and also we can figure out if the means in general are different or not. In this chapter we'll just talk about two sample tests, and we are going to skip one-way analysis of variance. So we'll explain in details confidence intervals and hypothesis testing about two samples. For one-way analysis of variance, that one will be discussed in the SPSS course. The objectives for this chapter are how to use hypothesis testing for comparing the difference between the means of two independent populations, the means of two related populations. Let's see the difference between two independent and two related populations. So the two populations might be considered independent or related. Related means dependent populations. Now for independent populations, in this case, sample 1 does not affect the results of sample 2. For this reason, we call it as independent sample. So sample 1 does not affect the results of sample 2. For example, suppose, as we mentioned, we have females and males. So here, the two groups or the two samples are independent because the student scores for females, for example, does not affect score for males. For this reason, they are independent. So since we have two different groups or two different samples, in this case, we have independent populations or independent samples. Now, for the two related populations, for example, in this case, suppose we have 10 persons. Person 1 suppose his or her weight 120 kilograms for the first item. The second item or second person, his or her weight is 135 kilograms. The third one, for example, 110. And suppose we have 10 persons. Suppose these are weights in kilograms. Now suppose these people or these students or whatever they are have diet for a period of time. For example, suppose they have diet for 3 months. So currently their weights are given by 120, 135 and so on. Then they have diet for 3 months after that. Then we measure their weights after 3 months. Now suppose the first person, his weight was 120. For example, his weight was in January 120. Now in April, for example, suppose 105 kilograms. The second person, suppose 120. The third one, suppose 95, and so on. Now, in two cases, we have the same individuals, the same persons. Person one, his weight was 120, and after a specific period of time, his weight becomes 105. So we have the same people, the same individuals for both weights. In this case, these two samples are called related samples. So for related samples, we have the same group, but we have different, or I'm sorry, we have repeated measures or repeated measurements. Another example for related samples. Suppose some patients have high blood pressure and they are using drug A. And we have some information about their blood pressure. Suppose first person, his or her weight, blood pressure 145. The second one, suppose 160 and so on. So suppose these people, these patients, use different drug, for example, drug B. And our goal is to see if drug B is more effective to reduce the blood pressure than using drug A. Suppose by using drug B after, for example, 3 months, the first person with high blood pressure, 145, becomes, for example, 130. The other one, suppose 145 and so on. So here we have the same patients. Patients took drug A, and after taking drug B for 3 months, for example, their new measures are given by 130, 145, and so on. So each person in this case has two values or two observations. One before using drug B and the other after. So if you have before and after, it means we have related samples. So any problem has before and after for the same people, the same individual. In this case, we have related samples. So we have to distinguish between two independent populations and two related samples. The other objective, we are going to use hypothesis testing for comparing the proportions of two independent populations. That's all for this chapter. We are going to skip the variances of two independent populations. So this one will be skipped. How to use one-way analysis of variance ANOVA to test for differences among. Among in this case means between more than two populations. So among means more than two. So here we are going also to skip analysis of variance as well as how to perform multiple comparisons and one-way analysis of variance will be skipped. So mainly we are focusing on the difference between two means and two proportions, two means for independent and related, and also we are going to cover hypothesizing for the difference between two population proportions. That's all for this chapter. So again, we are going to explain how can we perform testing for two sample tests. In this case, there are 4 cases. First, we will discuss hypothesis testing for the population means for independent samples. So in this case, we have mean 1 versus mean 2. So that's for independent samples. The other one also for the population means, but for related samples. By the way, sometimes called a pair samples. The word pair comes from, we have 2 values for the same individual. So 125, after that becomes 110, for example. So it's called pair. So in this case, we have same group before versus after treatment. The other type of 2 sample test is population proportions. In this case, we are going to test to see if there is a difference between 2 population proportions. The other type of 2 sample tests, population variances, variance 1 against variance 2. As we mentioned, we are going to cover population means for independent and related samples, as well as the population proportion. That's all, again, for this chapter. We have to start with the sampling distribution, actually, of the difference between 2 population means. In chapter 7, we talked about sampling distribution for X bar. And we said that X bar is a point estimate for mu. Now in this chapter we are interested for the difference between 2 population means. That means if we have mu1 minus mu2, in this case the point estimate of this difference should be x1 bar minus x2 bar. So x1 bar minus x2 bar is a point estimate for the difference mu1 minus mu2. So this one is a point estimate for mu1 minus mu2. It's clear that x2 bar minus x1 bar is a point estimate of or for mu2 minus mu1. So that's the point estimate of mu1 minus mu2 or mu2 minus mu1. Just x1 minus x2 bar is the point estimate for mu1 minus mu2. So again, our goal is to test hypothesis or form or construct confidence interval for the difference between 2 population means mu1 minus mu2. And the point estimate for this difference is x1 bar minus x2 bar. In this case, we have 2 cases. One is called independent or unrelated. The same meaning. Unrelated means independent populations. In this case, as we mentioned, sample selected from one population has no effect actually on the sample selected from the other population. As we mentioned, there are 2 groups, males and females. So group 1 does not affect group 2, males population does not affect the population of female. So in this case, we have unrelated or independent populations. In this case, there are 2 scenarios. sigmas unknown, but we assume they are equal. So sigma 1 and sigma 2 are unknown, but we assume they are equal. In this case, we are going to use something called pooled variance test. The other scenario, if the two sigmas are unknown, but they are not equal, in this case we are going to use something called separate variance test. So in this chapter we focus just on unknown sigmas, because in real life population variances are unknown, so we have to focus on this case. I mean, sigmas unknown, but maybe we assume they are equal, or we assume they are not equal. Now, the hypothesis test in this case, if we are talking about two population means, are again two-tail test, the same as we discussed before, or one-tail test. And one-tail has two cases, lower tail and upper tail. For example, if we are interested in two-tail test, we have to state carefully the null and alternative hypothesis in this case. So the null hypothesis should be mu1 equals mu2. It means there is no difference between the two population means. In this case, it means that the difference equals 0. So either you can state your null hypothesis by using this way, mu1 equals mu2, or the other way, the difference is 0. They are equivalent. Because if the means are equal, it means the difference is nothing, is 0. Against the alternative hypothesis, mu1 does not equal mu2, or the difference is not 0. So you may use the other format, maybe it's better, mu1 minus mu2 equals 0. Against the difference is not 0, or the other one, either one is okay. Now, for the one-tail test, there are two cases, lower tail or upper tail. Lower tail, it means under the alternative hypothesis, h1, mu1 is smaller than mu2. It's called lower test. So if mu1 is smaller than mu2, that means the difference between the two population means is negative. Because here mu1 is smaller than mu2, it means the difference between these two is negative. And as we mentioned before, h1 is the opposite of h0. So if h1 mu1 is smaller than mu2, it means under the null hypothesis, mu1 is greater than or equal to mu2. And as we mentioned before, the equal sign appears only under the null hypothesis. So here for the two-sided test, the equality here appears just on the null hypothesis, as well as for lower and upper tail test. For the upper tail test, again here we have mu1 is greater than mu2. It means the difference between these two population means is above 0, greater than 0. So that's the new scheme for formulating or stating null and alternative hypothesis. It's quite similar to the one we had discussed in chapter 9. Any question? So this is step number 1 for doing or performing statistical hypothesis testing. So again, there are two types of tests. One is two-tail. In this case, there is no direction. You don't know the exact direction of the two population means. You just say there is a difference between the two population means. In the other two cases, you know the exact direction. You may say that population mean for A is smaller or less than or decrease from the other one. Here, population A is larger or increase or whatever it is. So we have null hypothesis, alternative hypothesis, maybe two-tailed or one-tailed test. It depends on the nature of the problem itself. Now, what's about the rejection regions? Similar as we discussed before, if we are talking about two-tailed test, in this case there are two rejection regions, one to the right of alpha over 2 and the other to the left of the other side of alpha over 2. But here we have T alpha over 2 and minus T alpha over 2. And again, we are focusing on unknown sigmas. So we have to use T critical values. So we reject the null hypothesis the same as we mentioned before if this statistic falls in the rejection regions. In this case, if this statistic lies in this region or the other one, we have to reject the null hypothesis. That means if we reject the null hypothesis if T stat is less than negative T alpha over 2, or if T statistic is above or greater than T alpha over 2. So the same as we discussed before. That's for two-tail test. Now for lower tail test, in this case there is only one rejection region to the left side. It's minus T alpha. In this case we reject the null hypothesis if the value of the statistic or the test statistic is smaller than negative T alpha. So we reject if T stat is smaller than minus T alpha. On the other side, if we are talking about upper tail test, so your null hypothesis, your alternative hypothesis, always look at the alternative hypothesis in order to determine the rejection region. So if it is greater than, it means you have the area to the right. I mean, the rejection region should be to the right. If the null hypothesis, if the alternative hypothesis is negative, I mean smaller than 0, it means the rejection region should be to the left side. So here, the alternative hypothesis, mu1 minus mu2, the difference is positive. That means the rejection region is to the right side. So we reject the null hypothesis if the statistic is greater than T alpha. But here for the two-sided test or two-tail test, there are two regions. I mean, there are two rejection regions because there is no direction under the alternative hypothesis. So alpha should be split in half. So alpha over 2 to the right and alpha over 2 to the left side. So this scheme actually mimics or is the same or similar to what we have discussed in chapter 9. Any question? So again, we have to formulate or state carefully null and alternative hypothesis for both cases, 2 and 1 tail test. And the rejection regions, I think, is straightforward. Now, let's see what are the assumptions in this case. If the two sigmas are unknown and we assume they are equal. So we assume both sigmas unknown, I mean both population standard deviations are unknown, and we assume they are equal. The assumptions are, first, samples should be drawn randomly and independent. So samples are randomly and independently drawn. So we have to select random samples, and they are independent. So assumption number 1. The second one, populations are normally distributed. So we have to assume the population is normal, or both sample sizes are at least 30. So in order to apply the central limit theorem, so similar to the one we had discussed. So here, either the populations, I mean both of them, normally distributed, abnormally distributed, or both ends or both sample sizes greater than or equal to, so at least that. In addition to that, we have to assume that population variances are unknown, but we assume they are equal. So the assumptions are samples are randomly selected and independent, populations are normally distributed, or the sample sizes are large enough in order to apply the central limit theorem. In addition to that, population variances are unknown, but we assume to be equal. These are the classical assumptions for performing t-test when sigma 1 and sigma 2 are unknown, but we assume they are equal. Any question? Next, let's see how can we state the test statistic. Again, we are talking about testing for the difference between mu1 and mu2. So hypothesis for mu1 minus mu2 with both sigmas, sigma 1 and sigma 2 unknown and assumed equal. This statistic in this case is similar to the one we discussed, but there is a little difference in these two. The first one was this statistic was x bar minus the mean divided by s over root n. That's okay if we are testing for x0 mu equal, for example, any value, 3 or 4 or whatever it is. Here we are talking about the difference, testing or test for mu1 minus mu. So my t statistic equals, for one sample we have only a point estimate, x bar is a point estimate for mu, but when we are talking about the difference between two population means, the point estimate is x1 bar minus x2 bar. So here I should have x1 bar minus x2 bar. So this is the first term in this formula, minus. Here we have minus mu. But for the new scenario, we have h0, mu1 minus mu2 equals 0. So here mu1 minus mu. In most cases, we assume the population means are under 0. There is no difference between these two population means. So we are assuming mu1 minus mu2 equals 0. So it means this term cancels. If we assume there is no difference between these two population means, in some cases, might be the difference between these two equal, for example, A, and A is just a constant. In this case, you have to plug A instead of mu1 minus mu2. But most of the cases will have this classical one, the difference is 0. Divide by, this is the new term in this chapter, divide by the standard error of the estimate. Because here, if we go back a little bit to the t statistic, it's x bar minus mu divided by s over square root of n is the standard error of x bar. The same here, we have, standard error of this estimate. So the new term is, how can we find the standard error of x1 bar minus x2 bar? This one is given by square root of s square b multiplied by 1 over n1 plus 1 over n2. S square b is called the pooled variance. And the pooled variance is given by this equation. So first of all, we have to compute the pooled variance by using this equation, s square b equals n1 minus 1 s1 squared into minus 1 s2 squared divided by n1 minus 1 plus n2 minus 1. Now let's see if this makes sense or not, the pooled variance. Now, as we mentioned, there are two samples. The first one has sample size of n1. The other one has sample size of n2 with variances are s1 square and s2 square respectively. So we have two samples with sizes n1 and 2. Sigma is unknown, but we know the sample variance for each. Now suppose the two samples are mixed. Let's see how can we find the pooled. It's called the pooled, sometimes called the weighted variance. Look at this formula. n1 minus 1 squared plus n2 minus 1 is 2 squared divided by n1 minus 1 plus n2 minus 1. We know that s squared is the sum of x minus x bar divided by n minus 1. That's if we have only one sample. Now just cross multiplication, we will get n minus 1 s squared equals sum of x minus x bar squared. That's for the first sample. What's about the second one? We have two samples, so we can write for the first one n1 minus 1 s1 squared equal sum x minus x bar. This is for sample 1. For the other sample, we have the same equation but different data. So we have s squared equal y, for example, minus y bar divided by n2 minus 1. Now cross multiplication, you will get n2 minus 1 is 2 squared equals sum of y minus y bar squared. That's for the second sample. We are talking about, we are looking for standard error of the difference between these two. So now, the standard error, or let's compute first s squared b for both. Now, s squared in general, as we mentioned, is sum of x minus x bar squared divided by n minus 1. So here we have the first sum plus the second one divided by n minus 1 for the first plus n2 minus 1 for the second. Now this sum equals n1 minus 1 is 1 squared. The second sum is n2 minus 1 is 2 squared. Divided by n1 minus 1 plus n2 minus 1. So this is how this equation is formulated. So s squared is called the pooled variance. Because as we mentioned in chapter 3, the variance, the definition of the variance is the average s squared is the average of the square differences around the mean. And this is the same, because here we have sum of x minus x bar plus the other sum y minus y bar, all divided by n1 minus 1 plus n2 minus 1. This term can be written as n1 plus n2 minus 2. So this is your pooled variance. Now, sum x minus x bar squared equal n1 minus 1 is 1 squared. Yes, because we are looking for the difference or the variance first. The variance for x1 bar minus x2 bar. This variance is variance of x1 bar plus variance of x2 bar. So we have to add this together. But we are talking about the difference of the mean standard error of x1 bar minus x2 bar. Now, what's the standard error of x bar? Square root sigma over n, or s square over n. If sigma is unknown, we should have s square. But here we are looking for standard error of x1 bar minus x2 bar. So this equals, and sigmas are unknown, so we have s square b divided by, or multiply this case by 1 over n1 plus 1 over n2, because we have two different samples. So now the standard error of the difference equals square root s square b multiplied by 1 over n1 plus 1 over n2. So now the t statistics becomes, again we have x1 bar minus x2 bar minus the difference between the two population means divided by this term represents the standard error of estimate, this estimate, generally speaking, any statistic, for example, theory, is estimate minus hypothesized value divided by the standard error of this estimate. And it is statistic. If we are talking about one sample, in this case, we have only one estimate, so it's x bar, minus hypothesized value mu, standard error of x bar, which is s over square root. That's for one sample. Now for two samples, what should we have? If we are talking about two samples. Now the estimate for the difference. Now the difference is x1 bar minus x2 bar. Minus the hypothesized value. Under x0, we are assuming mu1 minus mu2 equals 0. That's the general case. I mean this special case. Sometimes suppose it's equal A or whatever it is, we have to plug A here. Divide by the standard error of this estimate. Now the standard of this estimate equals this one. So we have to divide by s square b multiplied by 1 over n1 plus 1 over n2. So this is your test statistic. Any question? So again, this is the estimate of the difference between mu1 and mu2. The other one is the hypothesized value. In most cases, this difference is 0. Divide by this amount is the standard error of this estimate. And the standard error is given by square root. It looks like square root of s squared divided by n. But in this case, we have two standard deviations. So s1 squared over n1 plus s2 squared over n2. But we are assuming that both sigmas are known and we assume they are equal. So these two are the same. So factor out. So here we have s squared 1 over n1 plus 1 over 2. And this one is called square root. Any question? Basically, we are going to use this statistic and the formula will be given. Either the pooled variance equation or the other one. Now, what's about the confidence interval? As we mentioned before, any confidence interval can be constructed by using general form, which is estimate, the point estimate, any confidence interval. Estimate plus or minus critical value times standard error of your estimate. That's in general. Estimate or point estimate plus or minus critical value times the standard error of your estimate. Before we had talked about confidence interval for mu. So in that case, we have x bar plus or minus t, then standard error of this estimate, which is s over root n. That's before. Now we are talking about confidence interval for mu1 minus mu2. Now my point estimate of this difference is x1 bar minus x2 bar, plus or minus. Critical value is E alpha over 2. since sigmas are unknown, times the standard error of the estimate. This value is square root 1 over n1 plus 1 over. So this is your confidence interval. By the way, this statistic has t-distribution with degrees of freedom equals n1 plus n2 minus 2. Because for one population, when we have one sample, your degrees of freedom is n minus 1. If we have two populations and we selected two random samples, your degrees of freedom is n1 plus minus 1 plus n2 minus 1. So add these should be n1 plus n2 minus 2. So this statistic has t-distribution with degrees of freedom n1 plus n2 minus 2. This is only if we assume variances unknown but they are equal. In this case, your degrees of freedom n1 plus n2 minus 2. So that's for the testing and the confidence interval approach. So if sigma is unknown and they are equal, your confidence interval is x1 bar minus x2 bar plus or minus c alpha over 2 square root s square b multiplied by 1 over n1 plus 1 over n2. If we are talking about confidence for mu2 minus mu1, we should have here x2 bar minus x1 bar plus or minus the same amount. Because both plus doesn't change if we start with 1 over n2 plus 1 over n1. But this one should be x2 bar minus x1 bar if we are talking about confidence interval for the difference mu2 minus mu1. And that's all. Any question? Yes. Well, in general, x1 bar and x2 bar are not equal. Because if we have two populations and you select two different samples, it makes sense that the two means are not equal. But if they are equal, it means your statistic is 0. And that's never happened in the real life. Maybe close to 0, but not exactly 0. Let's look at one example. A straightforward example. You are a financial analyst for brokerage firm. Is there a difference in dividend yield between stock listed on the New York Stock Exchange and NASDAQ? You collect the following data. So we have two data for two different stocks. One for New York Stock Exchange and the other for NASDAQ. We have a random sample of size 21 from the first one with standard deviation 1.3 and sample mean 3.17. The other sample gives the following results. The random sample size equal to 25 with mean 2.53 and standard deviation 1.16. So this is the information we have. Sample sizes for both sample means and sample standard deviations. So that means population variances are unknown. Assuming both populations are approximately normal, we have to assume they are normal because the sample sizes are less than 30. In this case, if they are smaller than 30 and the populations are not normal, we cannot use the t-statistic. T is used only if populations are approximately normal or n is larger. But in this case, the two sizes are smaller than 30, so we have to assume both populations are normally distributed or approximately normally distributed, or we have to use another test. So we are assuming both are normal with equal variances. The question is there a difference in mean yield? So there is no direction. Is there a difference? That means we are testing mu1 equals mu2 against mu1 does not equal mu2. So the null hypothesis, the difference between these two is 0, because it asks about is there a difference here. So we assume there is no difference. It means mu1 equals mu2 under the null hypothesis. Against the alternative hypothesis, mu1 minus mu2 is not 0. That means mu1 does not equal mu2. So either you state the null by using this way, mu1 minus mu2 equals 0, or mu1 equals mu2. Now, before computing the t statistic, we have to compute s square b. For s square b, this is the equation we have. Now, n1 is 21. So 21 minus 1 times s1 square. We have the sample standard deviation of 1.3 for the first sample. So this is quantity square. Plus, n2 was 25. Minus 1 times s2 square, 1.16 square. Divide by n1 minus 1 plus n2 minus 1. That will give the sample, the pooled sample variance, which about 1.5. Now, in this case, after computing s square b, easily you can compute the value of the test statistic by using this equation. Now, x1 bar minus x2 bar, x1 bar is 3.27, minus x2 bar is 2.53, minus. Here we should have mu1 minus mu2. Now, under h0, because the test statistic is computed only if x0 is true. So always, we compute t statistic under h0 is true. Always. Otherwise, we cannot compute the statistic. Imagine that the rule is compute the value of the statistic if h1 is true. Let's see what will happen. Now, if h1 is true, h1 mu1 minus mu does not equal 0. So what's the value here? You don't know. Because this difference is not 0. So what's the value? I don't know. So you cannot determine the value of the statistic under h1. But under h0, here we are assuming the difference is 0. So this statistic can be computed only if the null hypothesis is true. Otherwise, you cannot compute this value. Make sense? So maybe true and false problem ask about we compute this statistic under h0 is true. It's correct statement. In this case, we are assuming the difference is 0, so minus 0. In real cases, in most cases, we assume this difference is 0. In some cases, it might be, for example, it's the 3, for example, or 1. 1 makes sense. So we have to plug 1 instead of 0, if the difference is 1. But here the difference is 0, so it should be 0. So minus 0. Divide by s square b, this amount, multiplied by 1 over n1 plus 1 over n2. So 1 over 21 plus 1 over 25. That will give 2.04. So your t statistic in this case is 2.04. As we mentioned, since we are talking about two-tailed test, there are 3 different approaches for testing. One is called a critical value approach. The other one, a confidence interval, and the last one is p-value approach. So let's see 2 of these. Critical value approach. Keep in mind your t statistic is 2.04. Now, since it's two-tailed test, so you have 2 rejection regions, T alpha over 2 with degrees of freedom N1 plus N2 minus 2. N1 is 21, N2 is 25. So your degrees of freedom 21 plus 25 minus 2, this will give 43. So degrees of freedom is 43. Now look at the T table. 25. So it's 25 minus 2, so that will give 44. Now look at the normal, T table for degrees of freedom 44 under area to the right side of, since we are talking about alpha 5%, so the area to the right 0 to 5, the area to the left is the same. So we are looking in the upper tail for 0 to 25, and this amount is 2.0154. So this point 2.1054, the other is negative 2.10. So we reject the null hypothesis if your T statistics fall in this region, I mean if T statistic greater than 2.01 or smaller than negative 2.01. In this case, my statistic value is 2.04. This amount actually falls in this rejection region, so we reject the null hypothesis. So since T statistic is 10, which is equal to 2.04, is greater than 2.01, then we reject the null hypothesis. So the decision is reject 0 at 5% level of confidence or significance. Your conclusion, there is evidence of a difference in means. That means the mean of New York stock exchange does not equal for Nasdaq. So that's how can we use the critical value approach in order for testing the null hypothesis. Any question? So one more time. We have data for New York Stock Exchange with this information, and for Nasdaq. And we assuming here populations are normally distributed because the sample sizes are less than 30, and we assume sigmas unknown, but they are equal. So the null hypothesis mu1 minus 2 equals 0 against is not 0. We have to compute the pooled variance first, then we can compute the value of the test statistic. The value is 2.04. As we mentioned, there are three approaches for doing this test. One is called the critical value approach. Now, critical values plus or minus T alpha over 2 with degrees of freedom 44. By the T table, we got this result. So the critical regions are above 2.01 or below minus 2.01. Now your statistic falls in this rejection region. So we have to reject the null hypothesis. So my conclusion is there is sufficient evidence to support the alternative hypothesis. The other approach, confidence interval for mu1 minus mu2. Again, the formula is, he asked about, since we reject the null hypothesis, so this hypothesis is false. I mean, the difference is not 0. Can we be 95% confident that the mean of New York Stock Exchange is greater than Nasdaq? Let's see. Let's formulate or let's construct the confidence interval for mu1 minus mu2. This is your formula. So x1 bar minus x2 bar, if you go back a little bit to these two values, x1 bar is 3.27 minus x2 bar 2.53. The difference is this amount, 0.74. plus or minus T alpha over 2, the critical value we have here. So plus or minus this amount times the standard error of this estimate. You easily can compute this value by 0.3628, and you will end with this interval. Now, this interval means that we are 95% confident that the difference between the two population means fall between these two values. Now the question is, since we are testing mu1 minus mu2 equals 0, does this interval contain 0 or not? So the question is your interval contain 0? Contain 0, 0 star, this 0. Maybe it's 1, not 0. In this case, it's 0. Now, this interval, the lower bound is positive, the upper bound is positive, is also positive. So 0 is not inside the interval. So that means it's never equals 0. So we reject the null hypothesis. So since 0 lies outside this interval, I mean the confidence interval does not contain 0, that means we have to reject the null hypothesis. So if the rule of thumb is, if the confidence interval, in this case for mu1 minus mu2, contains 0, then we don't reject. We don't reject. Otherwise, we have to reject it's 0. But be careful, not always 0. Here we are assuming the difference is 0, but the difference, if the difference is 1, then ask yourself, is this interval contain 1 or not? But in this case, it's 0. So the question is CI contain 0 or not? 0 is outside, so we reject the null hypothesis. Now, do you think the mean of New York stock is greater than Nasdaq or not? Since the interval ends, I mean lower and upper bounds are positive, 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 so that means the mean 1 is greater than mean 2. So mean 1 means for New York is greater than the mean for the other one. If the interval is negative, negative, that means mu1 is smaller than mu2. If it is positive, positive, then mu1 is greater than. If it is negative plus, then if the interval starts from negative to positive, that means 0 lie inside the interval. So in this case, we don't reject. So the only time we don't reject is 0 if the lower bound is negative and the upper bound is positive. Because if we start, for example, from minus 1 to 2, for example, in this case 0 in the interval, I mean the confidence interval, contains 0. In this case, we don't reject. So again, the only time you have to don't reject is 0 if the confidence starts from negative to positive. Otherwise, you reject the null hypothesis. So in this case, 0 is less than the entire interval, means outside the entire interval. We can be 95% confident that the mean of New York Stock Exchange is greater than the mean of Nasdaq. Make sense? Any questions? Next time we'll talk, I will give the third approach, the p-value approach for conducting the hypothesis testing. Any question? So that's all for today.